אני אציג אותו באנגלית, אני רואה שיש כמה אנשים מחו"ל. I think it was like, what, you are 4 or 5 years ago when you stepped into my office one morning and then started talking with me about
יגאל, לא שמעו
you
קטע.
did your masters with Judith and with Dov, and I contact them and they told me that I'm very happy. Hey, I'm very lucky, sorry, that you're considering to do a PhD with me. And as it turned out that they were right. And the next thing was to take you over to Yehuda's office and see how we can fit you into the project that we have in the Dead Sea. And ever since then, I've been having a very enjoyable, stimulating, and happy meetings with you, and I've been learning a lot from you over the years. And I'm very glad that by now we start seeing the next step in your career, and I'm expecting you to continue to excel in the future. So please show us what you've done.
Okay, so thank you very much for that. I'm going now to mute everyone. And then I'm going to start sharing the screen. Okay, so can you all see the screen? You can nod your heads if you see the screen. Yeah, Yaki, Yaakov, you see the screen? Okay, great. So I want to talk today about hydroclimatic variability of late Pleistocene climate changes. And the way we did that was to utilize the sediments of the Dead Sea, which is somewhat related to what Yael has recently shown us an hour ago. So some of the things would meet in some places. I want to start off by acknowledging everyone who helped me along the way. So first and foremost, it's my wife and family. And then, of course, my supervisors, Yehuda, Efrat, and Igal, and also the members of the guiding committee, Achim Brauer, which is our colleague from the GFC, and Adav Lansky, which is our colleague from the survey. And of course, other friends and colleagues that helped us along the way, and I'm going to mention some of them as we progress. So this topic, this presentation today is focused on the topic of climate variability. And when we talk about climate variability, we first need to put some of the topics in context. So basically, when we examine aspects of climate change, we can think about it in several terms that help us make sense out of it. So when we talk about climate change in general, we're talking about some kind of a trend over a mean parameter. So that can be mean temperature, mean precipitation, etc. However, this mean, which is changing gradually over a long-term scale, which is usually around centuries to millennia, is usually accompanied by short-term changes. And these changes, they have several wavelengths. So some of them are what we call natural oscillations, and they vary at the scale of decades to centuries. And then on top of that, we can also see something that we describe as short-term variability. And this short-term variability is actually very important because this is one of the processes that eventually affects what we see. So this is eventually the proxy that we're interested in, whether it's precipitation or temperature. They are usually affected by the short-term variability, and this could have a large effect when it comes to what we're interested in. So what would be the problem with studying these kind of very short-term processes, and why is that important? So when we look at subtropical regions around the world, we know that they are characterized by high variability, meaning that the values of annual precipitation, they tend to change significantly from year to year. And they are also limited by the amount of water that they get. So there's a limited water supply, meaning that there's limited water resources. And they are expected to become drier as climate change progresses. So it is expected that as climate is becoming hotter, these regions will become drier. And this really requires a better understanding of climate variability because we need to know what can we expect when it comes to these kind of changes and what would be the eventual outcome of these changes when it comes to actual resources such as water and precipitation that we're interested in. The problem is that the available records are too short. So when we look at modern measurements, some of the longest records we have, they're about 1 century, a century and a half, and we have these at very limited localities. And when we look at the bigger picture, we usually have a few decades of measurements. So why is that a problem? Why are a few decades not enough? It's a problem because variability is non-stationary, meaning that it might change. So these short-term changes in the proxy that we're interested in, they could have some fluctuations over time. And in simple words, it means that the things that we've measured during the last decades, they do not necessarily reflect the way that the system actually behaves as it starts to change. This short-term variability could change as well, together with the mean parameters. And then the general idea is that we can find some geological archives, and we can use them to expand our knowledge and our understanding of these processes. So that's the general outline. So what do we mean when we say geological archives? Basically, I will show you one of them that we have here in the Levant. But generally, geological archives are the things that are usually studied by quaternary geologists. And the general idea is that these archives record environmental conditions. And in our case, we're interested in hydrological conditions. And some of them are also high-resolution archives. So these kind of archives, they can help us to understand why some periods are wetter, why some periods are drier, and we can really look deeper into the short-term mechanisms of what makes climate change. So to take this mean trend and to see what it is actually made of. However, these archives, they have some limitations because they are not direct measurements of the proxy we're interested in. They have limitations of resolution because they are geological archives, and they also have a limitation of interpreting the proxy. But this is something that all geologists have, and this was also one of the topics that Yael discussed, the interpretation of a proxy. So if we try to reflect this kind of previous graph that I showed on what we actually find when we utilize geological archives, so usually we have a good idea of the long-term trend. So we usually have some points that we can utilize to build the trend. And I will show you shortly the lake level curve for the Dead Sea and Lake Lisan. And I will show you that these points that demonstrate how lake level fluctuated, we can find them. However, they are of limited resolution. So they give us some idea about the mean, the long-term change. Then if we're lucky, we might get some information about shorter oscillations. And then if we are really lucky and we find good archives, then we can also try to uncover these very short-term changes, which we call hydroclimate variability. And you can see here in this illustration that in this case, the variability changes. So we have some periods that are characterized by a certain aspect of the system, and then it shifts into a different regime. And these shifts in regime, in order to get them, we need longer records than those that we currently have available from modern data. So what was the place that we can study these kind of records? We have a nice record in the Levant, and that's the sedimentary record of the Dead Sea. And the Dead Sea has a pretty big watershed where most of the precipitation comes from the north. And it's a terminal lake, and for that reason, its level generally reflects the water balance. So if we see that lake level is rising, this indicates that the water balance is positive. If we see that lake level is falling, this indicates that the water balance is negative. And again, it's a large watershed, so it kind of averages the processes that take place in the Eastern Mediterranean. It's characterized by two precipitation gradients, namely most of the precipitation that eventually reaches the lake falls in the northern part. So we can see here the isoyates, they're around 800, 600 millimeters. That's the modern measurement. And from the south, we have another phenomena, which is the phenomena of flash floods and debris flow, and they have impact on the central parts of the lake. Now, during the time interval that I investigated in this research, lake levels were higher, and the Sea of Galilee eventually was connected to the central basin of the Dead Sea. And this level is called, this lake is called Lake Lisan, and I will explain a little bit about it shortly. We are also lucky to have in our region a very good background. So we don't start off from nothing. We start from a really good position. During the last couple of decades, perhaps even more, if we consider also earlier works, many people studied the level of the Dead Sea, and they studied it again as a proxy of water balance. So here we see composition of the reconstructions from very different proxies of lake level. And basically, this reconstruction demonstrates that during stage 2, lake levels were much higher. So stage 2 up to 4, they represent the less glacial, and stage 2 represents the less glacial maximum. And again, we generally see that because lake level of the terminal lake reflects the hydrological balance, we can see that during certain millennia, we had a wetter climate on average. And we can see that within these periods, for example, within stage 2, we can see that lake levels also changed. And this indicates that within this overall wetter period, there were also periods that were characterized by different precipitation regimes. So where lake level is rising, we have a positive water budget. Where lake level is falling, we have a negative water budget. And this kind of reconstruction was built mostly using shore deposits. So it's quite a solid reconstruction of lake level for our region. And again, this was very important for our research because this provided the base on top of which we could have continued. So another benefit that we had working on the Dead Sea was the recent coring expedition of the ICDP. And this was really a big project that actually took place when I just started my bachelor's degree. So I was not there on the raft, but some of the people who are now listening to us were. And I know that my supervisors and their colleagues, they were some of the key figures leading this research, this drilling project. And basically, this is another good advantage. We have from the deepest part of the lake, where it's marked with the red hexagon, we have from this deepest point of the lake, a continuous record of nearly 450 meters. It was not exposed, meaning that it was always underwater. So unlike the exposures that were used for the previously shown lake level curve, these sediments were accumulated continuously, and they were better preserved, and you will see that in the cores in a second. it goes back over 200,000 years ago. So overall, it covers 2 glacial interglacial cycles, and including the intervals that's in between. So that's another important aspect that we have here. So let's look at this record, the sedimentary record of the Dead Sea, and see what it is made of. So here we can see the schematic reconstruction of the core. And we can see that roughly on a broad scale, sedimentation reflects the transitions between glacial and interglacial cycles. So the sediments record some kind of a limnological aspect of the lake that is eventually determined by hydroclimatological processes. And within these sediments, we have a few successions, a few sequences of sediments that are finely laminated. And those finely laminated sediments, occasionally, some of them, not all of them, but some of them, they were shown to be deposited annually, which means that we can utilize those segments that were deposited annually as a record for very short-term processes. So how does it look like when we actually zoom in? So here you can see an XRF scan of 2 sedimentary blocks. This was carried out by our colleagues at Potsdam, which have good knowledge on how to work with these kind of cores and sediments. And basically, within these sedimentary sequences, where we find those high-resolution laminated sediments, we can use them as recorders of processes in very high resolution. And the general idea is that these sediments, they are a proxy that reflect the water sources, the salinity, and the water balance of the lake. And we know at least 2 facies, 2 sedimentary facies that were deposited annually. There are halite vars, which will not be discussed today. And then there are the laminations of aragonite and detritus, and I will focus on these. And I will show you how we can utilize these kind of facies to reconstruct hydroclimatic variability. And these are very similar to the vars that we have seen in the exposures and that were studied previously. So we now have a complementary picture of the sedimentary phase from the deep lake that nicely complement what we already knew from exposures. So as a general reconstruction of their deposition, just to keep things simple. I know that there is still some discussion about some of the aspects, but as kind of a framework to our talk today, usually when the water balance is positive, which is usually correlated with high stands or rising lake levels, we see the deposition of aragonite and detritus laminae, not necessarily vars, but in some cases these are indeed vars, meaning that they're annually deposited. And then when lake levels are low, we see that halite accumulates. And then within the transition periods, we see all these kind of mixtures of things. So we usually get some detritus, aragonite, but there's also some gypsum and halite. So if we can get the broad framework of what kind of sedimentation regime we're looking at, we can utilize that to actually uncover climatic variability. And this brings us to the design or the rationale of the research, which is essentially that in order to investigate the variability of climate change in a subtropical region in the Levant, we decided to study the sedimentary record of the Dead Sea. Within this record, we utilized vars from the Dead Sea Deep Drilling Project. And we compare different episodes during which the water balance was different. So episodes during which lake level was rising or falling, which represents a different water balance, which essentially reflects a different mean climate. And then we utilize modern understanding, the way that we understand that precipitation behaves, to actually get some climatological insights on our findings. So we go into Lake Lisan, which is the less glacial predecessor of the Dead Sea. there has been plenty of research carried out on on Lake Lisan and its sedimentary record, and we focus on the time where its level changed dramatically, and we focus on the time for two reasons. First, we have good sediments from the core from that time period with good age control on them. And second, they reflect a very distinct and very different climatic change. So we think we can utilize these sediments that were deposited during this time interval to understand what climate change during the late Pleistocene was made of. So we took two segments, and under the idea, the general notion that the level reflects mean climatology, we took two core sections that are dated in a good fashion, and we decided to compare them. So one reflects an episode where lake level was rising, which essentially reflects the wet interval, and then the other one reflects an episode where lake level was falling, which essentially reflects the dry episode. So I have to say that this was a team effort. It was carried out in tight collaboration with our colleagues from the GFC in Potsdam, and they were also very kind to have us there for a nice summer school. And so I want to thank all of them and everyone who collaborated. So the general idea was to take these two segments, and that's how they look like, and under the assumption that the thicknesses of the laminae reflect, in a sense, the hydroclimatology of the watershed, to use the thicknesses and to perform some kind of a statistical analysis, a time series analysis, these kind of studies. The problem was that the images are not accurate enough. So we tried using the images and image processing techniques, but the thickness of the lamina is much less than 1 millimeter. And you need a really good camera to get images that are good enough. And even when we went there and we did it again with a very good camera, the images were just not good enough to actually see all the laminations and to get their accurate thicknesses. So we prepared thin sections. Again, this was done at the GFC. And then from the thin sections, the idea was to extract variability during those two episodes, and then to compare them, of course. So what did we find and how does it look like? So we take the image of the laminae and we put them under the microscope. The first thing that we noticed that was already described before was that aragonite lamina are clean, meaning that they don't contain other things. And the detrital laminae, detrital layers, they don't contain aragonite. So there is a clear separation between aragonite and detritus, and that's important for the way that we interpret these laminations. And the other two interesting findings were that, first of all, as you can see here, the core is green. It has a greenish color. And then when we looked at the microscope, we saw that this green color actually comes from very thin green lamination. And these laminations, when we use the fluorescence microscope, we saw that they are still red, which indicates something that is very close to chlorophyll in its composition. The other interesting finding was that some of these laminations, the detrital laminations, they're actually made of several sublaminations. And you can see here, for example, that this laminate is made of several sublaminae. And this again is important because we think that this reflects on the process by which these laminations form. So how do they form and how do we interpret these findings? So the general idea, and that's again the general consensus that has been around for several decades at least, is that during the time of Lake Lisan, aragonite deposition and detritus deposition, they actually reflect a seasonal cycle. So during winter floods that come into the lake from the surrounding streams flow into the lake. they bring in these kind of sediments that form, you can see here the images, they form plumes. And these sediment plumes are eventually carried by the waves into the deeper part of the lake, where they are deposited as detrital. And then after winter is over, during summer, aragonite precipitation takes place. And this happens through some sort of mechanism which was not fully resolved because it was only observed twice in the Dead Sea, and only one of these were actually followed scientifically. But the general idea was that during summer, there's a lot of sun and the water gets to a maximum temperature. And then there's a mechanism of degassing, which invokes a massive aragonite precipitation, which is also called whiting. And this is very similar to what we see in other lakes. So, for example, this is a monitoring study from a small lake in Turkey, and we see a very similar process. During spring, we see the deposition of organic material mostly, and some detrital material. And then during summer, we see the precipitation of calcium carbonate and aragonite. And then again, during spring, we see again another cycle start. So all these things together, along with the finding that the number of vars matches radiometric dating, they all together indicated that these are indeed vars, and that's the mechanism by which they accumulate. And this is important because this is one of the basic understanding we're going to use in order to interpret these findings. So again, just to give you a recap on what we found in these sediments, we found that there is a clear separation between detritus and aragonite, and we found that some of the detrital laminae, they are comprised of multiple floods, of multiple sublaminae. And what do we make of it? We think that during the times of Lake Lisan, when again lake level was much higher, so you can see here the shorelines of the lake. So the shorelines to the south was somewhere around here, and to the north it was somewhere in Lake Kinneret. So when we look at the location of the coring site, we think that the likely floods that are likely to deliver detrital material into the coring sites should come from the streams that flow directly towards the coring site, because again, the shorelines to the north and south were too far. And this, in our opinion, indicates that each of these lamina of the detrital laminations record a single flood or an individual flooding event. So we know that these sediments can remain afloat for a couple of days, but it indicates that a flooding event, that several flooding events took place during a single wet season. And these flooding events had to come either from the east or the west. So when we compare these two sections, here we see the number of floods, which is essentially the number of sublaminae in each detrital laminae, which make a year. We saw that when we look at their appearance over time, so we have here roughly 700 years recording an episode of rising lake level, which is on top, and another episode of lake level drop. And we saw that the number of floods, first of all, when lake level is rising, the number of years that have more than a single sublaminae, the number of years is much larger, meaning that when lake level was rising, we had more years with more sublaminae, meaning more years with more floods. And then we also saw that these high intensity flooding years, they are not distributed evenly through the time series. Rather, they are clustered into something that's around centennial scale. So we see that we have episodes where we have more years of increased flooding frequency, and then we have what we call the background years. So we see that during the lake level rise, for example, we have clusters of intense floodings, and then we have the background, which shows less flooding. When lake level was dropping, on the other hand, the amount of flooding was reduced, significantly reduced. And also the clusters are not as clear. So we marked here some clusters, but they're not as robust as for the time when lake level was rising. So how do we interpret these kind of findings? What can we say about the climatology that eventually formed this kind of sedimentary record? So we utilized modern observations, and we know from modern observations that most of the flooding events that are relevant for reaching the coring site, they are related to a synoptic system that's called a Mediterranean cyclone. And these cyclones, we know that they show some variability which is related to their properties. So when cyclones, for example, are very deep, or when they have a southern track, like we see here, so this is a very deep cyclone, and this cyclone has a very southern track, then they are more likely to induce flash floods that are relevant for reaching the coring site, and we're likely to see them as sublaminae at the record. However, when these storms are produced by cyclones that are either shallow, like this one here, or that they have a northern track, then the likelihood of them forming flash floods that could reach the coring site is reduced. And then we think that this mechanism could explain why the time of rising lake level could in fact reflect a time where cyclones were deeper and had a southern track, which also makes sense from the hydrological perspective, because we know that when the cyclones are very deep, or when they have a southern track, they're also likely to produce more rain and therefore to increase annual rainfall. So we see that this tying together of the mean change in hydrology and the storms frequency can actually be explained by, in modern terms, of synoptic scale systems. So that was the first approach that we took. And the thing that we wanted to utilize after we studied the detrita laminations was to utilize the aragonite laminations. So the aragonite laminations were studied previously by many people. And one of the suggestions that was made is that the aragonite laminations, they provide a quantitative proxy of annual inflow. So the idea was that because the lake is very poor in carbonate, during winter it is recharged with carbonate, and then during summer aragonite precipitates. And then if this is really as simple as it sounds, then you have a recorder of annual inflow. And if it's a quantitative inflow, then you can actually discuss numbers. So when you say that some periods were wetter, you can actually say how much wetter, which is very interesting to have in this resolution, not something that you can find easily. So we started looking into aragonites, and we also started reading about recent studies and previous studies. And so the first question we had was how much? So can we actually utilize the thickness of aragonite laminae as a proxy of annual inflow? If so, that's a great finding. And the other question which we asked, and that's related to some research that was recently conducted, was when aragonite actually precipitates, there is some discussion and some recent research that suggests that aragonite precipitation is not limited to summer, which is a problem because if it's not limited to summer, then you cannot really interpret this kind of proxy. And even the idea, the notion that these are reservoirs could also be questioned. So we started looking into the literature, and we saw that there is some kind of contradiction. When you look at modern studies of limnological geochemical proxies on the Dead Sea, and there were several studies that was done, starting with the one by Balkan almost 20 years ago, and then some other follow-up research. They suggested that aragonite precipitation in the Dead Sea, in the modern Dead Sea, is actually not limited to summer. And there was also a study that utilized pollen as kind of a proxy of seasonal deposition that also questioned whether or not aragonite precipitates only during summer. However, when we read about the available data on Lake Lisan, we saw that that everything we can read about Lake Lisan actually reflects that aragonite precipitation does take place during summer. So not only that it takes place after the winter, but that it's clearly separated from the winter. So we saw that aragonite and detritolamine are well distinguished, something that was previously described, and we also saw in the record. We saw that the detritolamine, some of them contain several multiple sublaminae, but they don't contain aragonite in between. So again, this indicates multiple flooding events with no aragonite in between. The only two reported whitings, they took place during summer, which again suggests that aragonite precipitation is somehow separated from winter and from the accumulation of detrital material. And always when laminate counting was carried out, it matched radiometric dating. And that's related to radiometric dating done with several methods, uranium, thorium, and C14, and basically they always came in within the error. So again, we have good evidence suggesting that these kind of laminations are indeed annual, but on the other hand, we have some studies questioning that. And I also showed you the example from the other lake, where we actually see that in modern lakes, that's the way it takes place, that these are indeed annual cycles. So the first thing we noticed when we started reading the literature was that Lake Lisan was not a Dead Sea. Again, it's something that Yael mentioned as well, but broadly speaking, Lake Lisan was only a third in its salinity than that of the Dead Sea, and perhaps even less, depends where in Lake Lisan, because it was quite a big lake. We see from isotopic data, both of carbon, but also from the green color of the cores, that the lake was actually characterized by a very active ecology. So we know that we had a lot of life going on and also primary production in Lake Lisan, which is not the case for the Dead Sea, where these kind of events are extremely rare and they only take place after very significant winters. And there are also the studies of other chemical proxies from aragonites that also suggested that the aragonites, they do reflect short-term hydrological processes. So all these things together, they indicated that whatever was happening in Lake Lisan and is in charge of the deposition of these laminations is probably not the same thing dictating aragonite precipitation under modern conditions. So after doing some reading, we found that organic compounds and ecological activity could have some impact about calcium carbonate precipitation. And we focused on a type of family of compounds that's generally called EPS. EPS are extracellular polymeric substances, and these are essentially some kind of mucus molecules that are produced by organisms. They're produced by organisms everywhere in any environment, but they're more likely to be produced, at least in higher rates, in environments that are difficult to live in. So where we see high salinity, high temperature, these kind of environments, creatures tend to excrete more of these compounds. And the reason is very simple. They use these kind of, so because they are relatively simple organisms, they use this as kind of a protective film. So they always release, excrete these kind of compounds. And the purpose is to eventually kind of separate them from the environment. So we read that these kind of compounds, which are again very common in aquatic environments, they could have implications also on the polymorphism of calcium carbonate, but also on the timing of calcium carbonate deposition. And there was another line of evidence from the sedimentary record of Lake Lissan that suggested that they could be relevant, and this is the fossil record. So when the fossil record of Lake Lissan and also the sub-recent Dead Sea was studied, a lot of evidence was found that these kind of organisms and all these organisms, the algae and the diatoms, and also other organisms such as cyanobacteria, they all produce extracellular substances. And therefore, we decided that that would be a good line of investigation to see if this could somehow relate to this contradicting evidence between modern measurements and the sedimentary record of Lake Lissan. So what was the rationale here? The rationale here was to sample Dead Sea brine and to reconstruct the brine that mimics the composition of Lake Lissan, and then to dilute them into a different ratios, which is essentially meant to mimic the dilution during winter, so mixing by floods, and then to monitor them for several months. And to some of the experiments, once we knew what kind of experiments can actually precipitate aragonite, we added EPS. So we took extracellular substances that we got from a colleague at the Silberman Institute, and he gave us some EPS that he collected, and we added them to the experiments to see what would be the effect. Our initial hypothesis was that this EPS would likely determine the polymorphism of calcium carbonate. And then the general idea was to monitor the solutions and to analyze the precipitates. So to go through all this process of monitoring the solution and to actually analyze the sediments themselves. So this was again a team effort. I had the honor of guiding two high school students that carried out some of this research, and they are really great, and we're very happy for this opportunity to introduce them into the world of research. And of course, other people that also helped us both in the lab, but also provided the compounds or provided some of the facilities that we needed to do the work. So what did we find out? First of all, we found out that the aragonite precipitates as the dominant polymorph. So when the Dead Sea brine was used, the aragonite was the dominant polymorph, except in one experiment where we found some magnesium calcite as well. And we also noticed that the morphology of the crystals slightly changes with dilution rates. So the more diluted the solution was, the finer the morphology of the aragonite was. And also to make sure that these kind of things don't change, that they don't alter, because in the process of extracting them from the solution and bringing them into the SEM, you have to dry them and wash them. So you cannot add brine to the SEM because then you won't see anything. It's all covered by halite. So we also took them to a microscope we have at the Institute, and we made sure that indeed what we eventually see in the microscope, in the SEM, is actually the thing that was produced. It's not some kind of alteration product. And we also compared them to available sedimentary sections. So we sampled the Masada section and also the Salim section, and also some crust from the modern Dead Sea. And we could compare the morphology of the crystals that we got from the experiments to the morphology of the aragonites that we actually find in the record. So we saw different morphology, and we saw that altogether aragonite was the dominant polymorph, except for one experiment where we also got some magnesium-rich calcite. When we inspected the yield, meaning the amount of aragonite that precipitated, so if you add in a certain amount of carbonate and you measure, for example, how much of it is lost, precipitated as aragonite, then you can get an idea on how much of the carbonate that eventually entered the lake could be translated into sediments. So again, when we inspected the yield, we saw that there's a similar yield between the Dead Sea and the Lake Lissan for similar mixing ratios. But we also noticed that there is some kind of threshold. So for example, in our study, once we crossed the the 40 or 50% brine in the mixing ratios, we saw that no aragonite precipitated. So you could take a solution that is 60% Dead Sea and flood solution. So again, it's a and you can wait for 3 months or 4 months and nothing happens. Precipitating, despite the fact that you have a positive omega take place from a thermodynamic point of view. Another thing that we noticed was that the incubation is also related to dilution. So once a certain dilution, aragonite precipitates relatively quickly and relative. The other thing that we found out that in all the experiments where we had no precipitation of aragonite, despite the fact that the control TPS, we did see aragonite precipitating. So we have could either limit or at least affect the speed of aragonite precipitation, but also the presence of also affect precipitation, namely it prevents precipitation, at least in our experiments. The other thing that we did was that we took the thickness from the exposure and we tried to do some kind of a mass balance. Is actually precipitated in the bottom of the lake, some kind of a uniform precipitation of aragonite, then we cannot really account for, let's call it reasonable inflow. So the amount of inflow that is at the higher bottom of the lake with aragonite is far above any reasonable. So it was 10 or 20 times of modern inflow, which is not really reasonable. So how can we resolve that? So again, I remind you, we were talking, and we're talking about the contradicting evidence. So we try now to a model that explains it. So during the time of lake, there was a strong seasonal control over aragonite precipitation. Because of the high precipitation and the high level of the lake, in winter, we had a lot of inflow, a lot of primary production, and therefore the production of the body. And then during summer, increased evaporation, introduced the carbonate-rich epilimit into the metalimnion, and the degradation of EPS facilitated the precipitation of aragonite, and we therefore think that the mechanism that separates aragonite precipitation from detrital is probably the organic process. We see a very distinct process, namely its inflow is very limited. It experiences any, doesn't reach the dilution threshold that is necessary for aragonite. There's also no primary production, so there's no EPS present with aragonite precipitation, and therefore we also cannot be considered as an analog for understanding aragonite precipitation in Lake Lisa. So just to summarize, and that's the final slide now. I know our time is over. So the variability of opposing late Pleistocene climate changes was studied using the high resolution sedimentary archives of the Dead Sea core. The flood frequency was found to be non-stationary and exhibits clustering. The frequency of floods was found to correlate with mean precipitation, which essentially indicates that the mean climate is actually made of the frequency and intensity of the storms that make it. The multilaminate detrital laminate that we found and the absence of aragonite, they further strengthened the notion that aragonite precipitation was distinct from detrital sedimentation. And we think that this is related to dilution and to biological activity. The aragonite laminae, unfortunately, were found to be too thick to be accounted for only by inflow. And we therefore think that this is reflecting either inhomogeneous sedimentation of aragonite or some other flux of carbonate into the lake. We considered, based on literature review, we consider the oxidation of organic material as a relevant flux of carbonate. So this would be one of the effects of sulfate reduction through organic material oxidation. One of the effects would be increase in carbonate content and alkalinity, which would also contribute to the thickness of aragonite laminae. But it seems at least that they do not quantitatively reflect. So we cannot, unfortunately, take the thicknesses of aragonite and directly reflect them, directly convert them into inflow. So this is it. This was the general purpose of the talk. We wanted to investigate what climate change is actually made of, and we took some segments where we have a good control on the centennial scale process, which is reflected by the lake level. In the sediments, we are able to study the annual scale, and we were even lucky enough to find out that in some cases, we can also uncover the seasonal and the event scale as well. And again, I would like to thank everyone who helped us along the way. So again, a big thank you to my wife and my family, and of course, to my supervisors who were always there for me and always helped me basically do what I thought that I would like to do, but also were there to guide me when I started straying too far off. So, and thank you, of course, for coming and listening. I don't see any activity, so I'm not sure if I'm talking to myself now. I see Yaakov now is moving. Okay. So, thank you.
Come on.
Yoav, thank you very much.
כל הכבוד.
Okay. Questions, please. Questions.
Yoav, I love your really detailed examination of the laminae there. Having done all that very fine work, is there any chance that there's some faster, like XRF scanning or something that could be done on a scale that shows the floods that you mapped on the thin sections?
Yes,
that's better than the images?
So we tried that actually. I was there in Potsdam recently, about a year ago, for a couple of weeks, and we took some blocks and we tried to actually compare them. But unfortunately, even the finest, I mean, recently the most expensive device is the one that gives you these maps. Even that doesn't go into the resolution that you can actually go in with a microscope. So unfortunately, the short answer is no.
יאקי, יכול לשאול?
כן, בוודאי.
First of all, I want to give a kind of historical comment. And Bibi Niv, I remember that about 25 years ago or more, when I started to work on the Lisan formation, and of course we went to Bibi Niv to ask for his advice. He told me that always, in order to distinguish between the Lisan and the Holocene, the Lisan is green, and the Holocene is not green. So that's going back to Bibi Niv. That's an historical comment. Now, my question is that I don't know, probably you try to do it, so maybe you can elaborate on it. But if we are talking about Potsdam, as you know, Sushma Prasad was doing a detailed study with the time series analysis of the Lisan formation on the exposure. And the question, if you made the comparison between your segment and her segment.
Yeah, so the short answer is not yet. We're now working on a more detailed time series approach. We had some issues with, this is the plan for the few upcoming months. That's the short answer. We tried to do that in a certain way that did not work. We are now working on another approach to try to do that. So hopefully this was our original plan, was to compare our findings with the deep core. So hopefully we will have some answers in the upcoming months, and I will let you know.
It's good for the Corona time.
Yes.
The other thing, and you are probably aware, and it's related to your conclusion, I agree with it, that the Dead Sea, the Holocene Dead Sea and Lake Lisan are very different. And in the recent works of Nurit and Ilan, and you know, they really show that, and Boaz, right, the paper of Boaz, that there is a significant freshening of Lake Lisan, which is going deep into the equilibrium. So when we are talking about Lake Lisan, then there is a significant freshening of the entire water body that is going deeply into the equilibrium. And part of the material comes probably from the dissolution of Mount Sedom that should be considered.
Yes, so we used some of these papers. We used them in our interpretation of the findings. And yeah, we think that the reason that it behaves much differently is because of this dilution. So we are aware of it, and we used it in our discussion as well. But what was the question? Maybe I missed. Okay, it's a comment.
Okay, any other questions?
Yaki?
Okay, Nadav, Kadima.
Okay. Hi, thank you very much for the talk, Yoav. It was very nice. And I want to ask you about the lamina, the trital lamina. So if we think of their source, these are point sources, right? Stream out, and then they spread over the water surface, and then finally they will settle. So my question to you is, so first it will naturally have lateral gradients, and my question to you is, now when you are finishing your PhD, where do you see the big unknowns regarding these laminas and their lateral distribution, and also how it affects maybe your analysis when you take only, let's say, one core and then you count the laminas and so on? Did you miss some events, or maybe you have over thickening, or maybe there are some other processes that bring the trital material? So my question to you is, what is your vision from nowadays about the knowns and unknowns regarding these laminas?
So that's a very good comment. This is one of the reasons actually that we realized that using the thickness itself of the detrital laminations is not a useful proxy, because it contains too many complications. What we're doing right now with the help of Francesco is to think of these lamina as kind of an accident. So these lamina, they actually record the events that were big enough and located in the right place to be documented in this specific site. So we try to change the approach from actually looking at it at the number, and to directly reflect, to think of it as directly reflecting the number of events, as to something that reflects the number of events that had crossed over the accidents that was necessary to reach the coring site. So if you're asking me about future research, I think the best thing would be to have some kind of sediment trap data, but that's now pretty much impossible in the Dead Sea. Or maybe to have some more cores from other deep places to see how they behave, you know. But it's true that that's one of the limitations. That's one of the limitations when we interpret these kind of proxies. We know that we only get a fraction of the data of the processes that actually took place. We don't get all of them.
Okay. Who else?
Yoav, thank you very much for a very nice talk. Could you reiterate concerning the assumption that the laminae are indeed varves? For example, could a big dust storm during the summer separate two aragonite layers, or is it possible to have a year without any aragonite deposition? How confident are you that each aragonite layer indeed represents one summer?
Okay, so the short answer is that we cannot really resolve it in 100%. We can look at the majority of the evidence and consider what makes more sense. When I first was looking at this finding of multiple sublaminae, I was in Potsdam and we had a meeting, a discussion with the group. And one of the guys was Novacek, who was working also with Ron and Moti and Yael. And one of the things he told me, I thought about the same questions that you just asked. And he's a guy who has a lot of experience with lakes. And he told me a lake does not change its skin within a single year. So a lake operates on some kind of scale. So it operates for several decades, several centuries in a way, and then it could maybe change. So basically this interpretation of VARs is based on a lot of previous studies that were carried out. And I think the strongest evidence, except for the comparison with other lakes and monitoring efforts, the strongest cases, the strongest evidence is actually the VAR counting. Every time someone counted the number of VARs and compared them with dating, it always matched. So if you think that aragonite precipitation is random, you know, there was some suggestions that it takes place several times every year. The chances of having that it constantly matches, and when this radiometric dating is done in several ways, are very small. So having this correlation between the number of VARs, the number of laminae, and dating is very small if they are really not related. So that's our general understanding, but of course we cannot know for 100%. It's also supported, the summer precipitation theory is also supported by, maybe I have that in an extra slide, it's also supported by the stable isotope composition. So the stable isotopes also reflect increased evaporation and high temperature. And it's also reflected by the recent observations. So the modern observations, I'm going to show now so that's the measurement from the Dead Sea by B.D. Neve. And they actually recorded the whiting event during the highest temperature. So that's the best we have. We cannot really say for sure that that's the case, but we think that the majority of evidence point at this conclusion. So we hope we're right, but of course, you know, someone might find something else in another decade, and that's our understanding of the archive.
I just want to add to Yoav's answer and actually extend on it, because what Yoav said in the counting, I want to elaborate on it. Sushma Prasad actually took the entire White Cliff, 8.8 meters at Masada, in thin sections under the microscope, and she counted all the lamina of 8.8 meters, but also in overlapping. So in two rows, not only in one, like you do two cores in these exposures. And she counted all the lamina, and then also did radiocarbon ages. And then later Adi Torfstein came and did uranium-thorium ages, and the lamina, the counting curve of Sushma Prasad lies on the radiocarbon and the uranium-thorium ages. So as Yoav said, it's not 100%, but there is nothing like this in the world. So at least in Masada, we can put our neck that for between 29 or 28,000 years ago to 17.5, it's valves. These are annual lamina.
Great, thanks.
Okay, last question, if anyone has.
Wait, moreover, I want to add to it another thing. And the other thing that Sushma was doing, she compared her time series analysis and the peaks to the Greenland ice cores, and she could show one-to-one correlation with the peaks in the Iceland in the Greenland ice cores. So Yoav is right, and I think these lamina are valves.
Okay, last question, anyone else? Ariel, we don't hear you. I thought you said something. Ariel Hyman. Okay. No one. So thank you, everybody. And it was very successful, I have to say. Maybe we will continue with it. We'll see. We need to think about it.
You didn't notice when the Chinese were disturbing Yoav talk, right? You were sleeping at the time.
Right, so I want to thank you everyone for joining today, and I wish you all good health to you and your families, and I hope to see you soon when things get back to normal, hopefully. So,
Bye-bye.
bye-bye.
Thank you very much. Bye-bye.
Bye, thank you.
Bye bye.